Hey y'all, and good morning, afternoon, or night, depending on where you are in the world. My name is Hannah. I'm a graduate student at the University of Utah. Today I'm talking about a paper I wrote in undergrad last year, along with Jim Dinan and Brian Larkins. As suggested by the title, this paper is about optimizing the work stealing process with structured communication operations. So what is work stealing? Work stealing is a form of dynamic load balancing where a problem is decomposed into a set of tasks. And when one process completes all of its tasks, it will steal tasks from another process until all of the tasks in the entire system have been completed by one process or another. Dynamic load balancing is often necessary when you have problems with sparsely populated data or inherent irregularity within the algorithm. Which don't lend themselves well to static load balancing. So dynamic load balancers have the ability to, at runtime, look at the current state of the system and based on that, determine how to balance or distribute work. So next we have an example of work stealing with 3 processing elements, computing a combination of both short and long tasks. So obviously the short tasks get completed first, leaving process 1 idle with nothing to do. So it can take work from process 0, and all of the processing elements in the system will just balance the load until completed. So both the Scioto split deferred copy queue and SWS, our new implementation, use a ring buffer with a local queue and a shared queue. The local queue, the tasks in there can only be processed by the queue that owns them, and tasks in the shared portion are exposed to the world for any other processes to come and steal. Typically, tasks are added to the local portion of the queue, and as shown here, they will wrap around automatically when you run out of space. All right, so for managing the split point of the queue, that's where the division is between the local and shared tasks. We have 2 operations, a release, which moves the split point into the local portion of the queue, exposing more tasks to be stolen. And the reverse of that, which is an acquire, which takes back tasks so they can only be processed locally. In the context of our work, understanding these 2 queue operations is important because they often overlap with remote steals. And if the proper synchronization mechanisms aren't in place, bad things can happen. Cities will burn down, who knows? So work published previously defines the split queue with deferred copies, dubbed SDC, to be a highly scalable and efficient algorithm for work stealing. This is the queue implementation we're doing all of our performance comparisons against. So under SDC, stealing is a 6-step process. First, the initiator, the process that wants to steal tasks from the target, will lock the queue so that the metadata doesn't get corrupted. It uses that to determine how many tasks can be stolen. Once it's done that, the initiator updates the queue, the metadata on the target, so that the next process that comes in will read the correct values and not like try to steal the same tasks. And once that metadata is updated, it unlocks the queue. And since it's updated the metadata, it can now steal those tasks, meaning copy over all of the memory without the lock. And then once the tasks have all been copied, it updates the target queue with the steal completion progress. So our work builds on the Scioto work stealing framework and demonstrates improvements in the time needed to complete remote steal operations. So a key insight was that by using a compact representation of the task queue metadata, that we can safely operate on it with a single 64-bit atomic operation rather than needing to use locks. And this representation also allows us to combine the process of work discovery and work stealing into a single step. And this shows the greatest performance impact in programs with short tasks and or highly irregular workloads, since they're the ones that are most impacted by the load balancing overhead. We dubbed our implementation SWS for structured atomic work stealing. Like the SDC implementation, it uses a steal half heuristic to determine the amount of tasks to be stolen. Prior research has shown this to be the most effective stealing technique. So what SWS does is it takes multiple pieces of metadata and fits them all into a singular 64-bit integer, since this is the largest value that can be operated on by atomic operations. So what this allows us to do is take the 6 steps stealing process and bring it down to 3 steps. So there's an atomic fetch and add for getting the queue metadata and incrementing the steal counter. Then there's the actual copy of the tasks themselves. And then lastly, an atomic fetch on the completion array on the target to indicate that the work has been stolen, and it would be safe to reclaim that queue space on the target side. So in that 64-bit integer, we have 4 key pieces of information. The attempted steals is how many steals have previously been attempted on that target queue by other processes. And then we have the initial tasks in the shared portion of the queue, as well as the tail of the queue at the time that those initial tasks were released. And then we have the valid bit, and that's set by the owning queue when it is in the process of performing an operation that would make it unsafe to do a remote steal. So when we read this value, and if the initiating process sees that the valid bit is set, it will immediately return without trying to steal any tasks. A small modification was made to the valid bit in the final version that we will look at in a bit, pun intended. So now we're going to walk through what a steal operation looks like under SWS. So to start, the initiator of the steal will do an atomic fetch add that uses a mask value to increment the attempted steal counter. And that's all we need to do so that the next process that comes to steal from that queue can do all of its stuff and determine the amount of tasks to steal without waiting on the currently stealing process. So we read this value, the initiator sees that 150 initial tasks were given to us. And because we're working with the steal half heuristic, we know that that results in the following sequence of 9 steals shown on the slide. So the initiator is going to steal the 3rd block of tasks, which is 19. And that begins at the index of the tail plus the amount of previously completed tasks, which again, since we're operating under steal half, we know to be 75 plus 35. So then the initiator copies all of the tasks into its local queue, and it updates a completion array on the target. So we ran into a couple of little roadblocks with this project. The first one being that since we're fitting everything into a 64-bit integer, that leaves 24 bits for the attempted steals value. And if work is sparse in the system, pretty much all the processes might be running around trying to steal. And so the attempted steals value can get really high. If that were to get too high, we could have integer overflow, and it would obviously corrupt the entire 64 bits. So we added steal dampening to solve this. Another thing we did was completion epochs. So steals can complete asynchronously. Just because, for example, 2 steals have been completed, you don't know if they're steals 1 and 2 or steals 3 and 17. So under the initial implementation, a local process would not be able to reclaim queue space until the entire sequence of steals had been completed. So steal epochs remedy this by introducing multiple completion arrays, which you can see is a bit different, literally. Please appreciate the pun. I don't have time to go over these right now, but there's more on them in the paper. So experiment evaluation. All of our tests were run against the previous IOTO implementation, the split queue with deferred copies. Results showed that since we have reduced communication overhead, we have faster steals, which means more processes doing work rather than looking for work. So first we evaluated the raw steal performance between SDC and SWS, and then we used 2 HPC benchmarks used in other dynamic load balancing analysis, the bouncing producer consumer and unbalanced tree search. So this graph shows the time taken to steal work from another process with 2 different task sizes. We can see that with smaller volumes of tasks, SWS performs over twice as well because of that reduction in communications. As you approach the larger steal volumes, the time taken to complete it is dominated by the transfer of the tasks themselves rather than the stealing overhead. So that's why those get closer together. So here we have the relative performance of SWS over the SDC baseline. The bouncing producer consumer has larger tasks, so you can see that those are very similar, but as you scale out in process count, it becomes somewhat noticeable. But then with UTS, we see consistently the overall program runtime is about 10% better with SWS. So another thing we found that because processes are spending less time communicating and there's less synchronization, they also spend less time searching for work. Obviously, that's significant because if processes are spending less time searching, they're spending more time actually doing the work and getting the program done. So this is the variation between runs. All of our stats were gathered by averaging 10 runs of the benchmarks. So we have the relative standard deviation, which you can see is pretty consistently under 0.2%, which means that our results and the program performance overall is extremely consistent. All right, I guess I'll conclude by giving a special thanks to the NSF, Exceed, and NVIDIA. And I guess we can take questions now.